Okay, the next reaction we're going to cover is called the Robinson annulation reaction. It's one of my favorite reactions in the book because it ties together a lot of the chemistry that we've learned into one jumbo reaction. Essentially what it is it's a Michael addition reaction that we just learned about, followed by an intramolecular aldol condensation. And if you remember, an intramolecular reaction is a reaction where something attacks itself. And in the process, we can form new rings. So in this example reaction I've shown, you can see that we've actually formed a second ring system. And this is hugely important when you're making molecules like steroids. If you're in a pharmaceutical lab and you need to make a steroid, steroids consist of multiple fused rings. And this is a strategy that can be used when making new rings. As you can see, it looks complicated, but every single step is one that we've learned already. So let's go through the mechanism slowly and see if we can figure out how to get from these starting materials to this product that's a fused ring system. And we've got a handful of reagents in solution. One of the reagents we have is this diketone. We have hydroxide as our base, and then we also have this alpha-beta unsaturated ketone. And the fastest reaction in chemistry before anything else can take place is going to be acid-base chemistry. If we ask ourselves, well, where's the most acidic proton? It's definitely going to be one of these two that are in between the carbonyl. Because if we pluck off one of these protons, the resulting conjugate base is highly resonance stabilized. And what I mean by that is we would get a negative charge on this carbon, and this negative charge could be shared with that oxygen, or it could be shared with that oxygen. So that negative charge is going to essentially be delocalized across three different atoms, which means it's going to be really stable. So when we do that, we're going to create this highly stabilized enolate. So let's make a note. And this is just referred to as our Michael donor. And we also are going to have our unreacted alpha-beta unsaturated ketone in solution along with our water. And if you remember, a Michael donor, meaning this enolate that we've made right here, when it reacts next, it prefers to add to the beta position. So if we have a beta position off of an alpha-beta unsaturated ketone or aldehyde, that's exactly where that Michael donor is going to react. It's going to react there rather than the carbonyl carbon. So in the next step, our Michael donor is going to attack in, and it's going to kick electrons all the way up to this oxygen. So let's go ahead and draw our next intermediate. When we do this, we create a new carbon-carbon bond, and we're left with an enolate. And what I mean is this portion of the molecule is still an enolate, and we know that enolates under equilibrium conditions usually aren't that favored. They prefer to tautomerize back to their ketone. So let's go ahead and show that enolate going back to the ketone form. And it can do that fairly easily by stealing a proton back from our water. All right, so now we've got our Michael addition product. And during this reaction, we've regenerated hydroxide too. So if we have hydroxide around, we could consider finding our next most acidic protons. And we actually have alpha protons in a variety of positions. We've got an alpha proton here. We've got two alpha protons right there. And we've got three alpha protons right there. Well, if we look at our product, you can see quite clearly that in this product, we need to form a new six-membered ring. So let's assess which of these alpha protons could potentially give us a six-membered ring. So if I were to, let's say, remove this alpha proton, let's imagine what this would look like. And you don't need to include this in your notes. This is just a mental exercise. If we were to do that, we would have a negative charge off of that position, right? And that negative charge, that enolate, could attack into another CO double bond. So let's imagine this, right? This negative charge I'll put as carbon 1, then 2, and then 3, and then 4. Theoretically, this could attack in right there. But if we were to do that, we'd form a 4-membered ring, which is just not very likely. That has too much ring strain associated with it. It's a lot harder to make a molecule with 90-degree bond angles when it prefers to be 109.5, right? So while we could deprotonate there, it doesn't get us to that 6-membered ring that we are clearly observing as our product. So it's probably unlikely that we're going to go after that alpha proton. Okay, so let's take a look at our other alpha protons. Let's imagine if we pluck off one of these, what would happen then? Well, if we were to pluck off one of those, we would get a negative charge right there. And again, I'll label this carbon 1. It's obviously not going to be able to attack in right there. That just won't occur. But maybe it will attack into this carbon. So that would be 1, 2, 3, 4 carbons away. So like I said before, one could theoretically show this reaction where it attacks in right there. However, we just said we don't want to form 4-membered rings. The ring strain is just too severe. So let's go ahead and erase all of those. And we know that those alpha protons don't lead to the product that we're observing, which means that the remaining alpha protons in blue must be the target protons. They're the only ones that would explain the formation of this product that we're seeing up here. So let's deprotonate one of them. When we do this, we're going to make a new enolate. This will be under equilibrium conditions, but just for the sake of simplicity, I'm going to draw everything with one-way arrows because the net overall reaction isn't under equilibrium. And we'll get a enolate, and we'll also have water floating around. All right, good thing with this enolate is it's 1, 2, 3, 4, 5, 6 carbons away from another carbonyl, which is ideal. That's what we want. So this negative charge will attack into that 6th carbon and kick electrons up to oxygen. I really like numbering my rings just so I can keep track of where everything's at. So carbon 5 and 6 were off of the original ring. So I'll put 5 and then 6, and then we'll go through and we'll say 4, 3, 2, 1. All right, off of carbon 6, we still have a bond to our oxygen, but now that oxygen has a negative charge. And then when we go over to carbon 2, we should still have that CO double bond, right? It's still there. So I'm going to go ahead and include that CO double bond, and really that should be it. We've formed our new 6-membered ring. We've accounted for all of our atoms. Everything's at the correct position. All right, but at this point, we're not quite at our aldol addition product because this intermediate is not neutral. So what we need to do is we need to make it neutral by stealing the proton back from water. So we're just going to have this alkoxide steal that proton back. By doing this, we're now at our aldol addition product. Like I said, aldol addition products can be favored under moderate to low temperature. However, if there's high temperature, we will actually kick off this hydroxide and make an alpha beta unsaturated ketone. So let's figure out which alpha protons are adjacent to this OH group. And this gets a little bit tricky. We've got an alpha proton right here, right? This proton is alpha to that carbonyl, so that is a potential target, and that alpha proton is next door to that OH group. Furthermore, we've got these two protons right here and here. And those protons are alpha to that carbonyl group, also adjacent to the OH group. So now the question is, which one of these will we go after? And I'll show you a few different options here, but let's try the first option, which is, let's go grab one of these. And when we do this, we're going to make a negatively charged enolate. We're still going to have this alcohol on here. And then in our next step, if we have heat, in fact, let's even include the heat symbol here just for thoroughness' sake. If we have enough heat, we can kick off this hydroxide as a leaving group. Let me clean this up a bit. And our byproduct in this reaction is going to be water. In fact, let me just slide this down and get it a little bit out of the way. All right, the benefit of doing this, like I said before, is we've extended the conjugation of the CO double bond. That's one benefit. And then the second benefit is we've actually increased disorder by kicking off a small molecule. In this case, by kicking off hydroxide, we've increased the entropy of the system. So this is one potential product, and in fact, this is the product that we observe. But I remember last year, one of my students asked me, well, up here, you went after these alpha protons. Why didn't you go after that one up there? I wanted to show you really quick. And again, this is one where you don't need to include it in your notes. This is just for fun. But let's imagine what would happen if we grabbed this proton. If we did that, we would get a different enolate. Where we'd have the negative charge up here. We'd have hydroxide, and then we could say, well, if this is all done under high temperature, then couldn't this negative charge clamp down and kick off hydroxide this way? Well, let's take a look at this product. If we did that, we would still get an alpha-beta unsaturated system. We would still kick off water, and we'd still have hydroxide. So a lot of students look at this and they say, well, isn't this just as good, if not better? And in fact, my student last year said, hey, this is a tetrasubstituted alkene. This is only a trisubstituted alkene. Why is this not the product, right? Well, it actually gets into kind of an obscure rule. And this obscure rule is directly related to bicyclic ring systems. Let me clean this up. And what the rule is it says that we shouldn't form double bonds at bridgeheads. So let's make a note of this. Not favorable. And then we'll say avoid double bonds at bridgeheads. So when we do these reactions, even though it is tempting to pick this product as the desired product, this one's really not favorable because it results in a double bond touching one of these carbon bridgeheads between the two rings. It's just not observed. This is called Brett's rule. It works for nearly all fused ring systems. Under very rare circumstances will you ever see a double bond forming at a bridgehead. That means that this product over here is definitely going to be our major product because we don't have a double bond going across both bridgeheads. All right, I hope that makes sense. If you have any questions, feel free to email me.